So I'm Nicholas, and I'm going to be talking about some lessons that we've learned from evaluating the robustness of defenses to adversarial examples. So the way I'm structuring this talk is I'm basically going to be working backwards. I'm going to start by defining adversarial examples. Then I'm going to tell you about defenses to adversarial examples. Then I'll talk about what it means to evaluate their robustness. And then finally, the lessons we've learned from doing that. So to make sure that we're all on the same page with adversarial examples, the standard setup goes something like this. You have an image, which all of us recognize correctly as a cat. And indeed, a state-of-the-art neural network will get it right with something like 88% confidence. And it turns out that you can introduce a very small perturbation that basically none of us as humans can recognize to get a new image that looks something like this, so that this image here is recognized incorrectly by the same neural network that gets the other one right, with 99% confidence with the label guacamole. And so this is the problem of adversarial examples, is that these two images, which are indistinguishable to us as humans, are completely different objects as far as a state-of-the-art neural network goes. Now, adversarial examples are not only a problem on images, they also exist on text and on malware classification and on audio. But for most of this talk, I'm focusing on images just because they're nice to show on a slide. OK. So why should we care about adversarial examples to begin with? There are basically two reasons why. The first reason is we want to make machine learning robust. Fortunately, in a security audience, I don't really need to justify this fact too much. We're going to be using these in security-critical situations. Ideally, they should behave robustly. But even if you don't care about the security aspects, which probably is none of you here, you should care about it just from the machine learning side, because ideally, we would like to make machine learning better. And adversarial examples give us a very nice case study where humans do very well. Today's systems do very, very poorly. And if you see this gap as being something which is worth closing, then maybe you should study adversarial examples for that reason only. So there's one more reason to think about adversarial examples. So this is a plot of the number of papers on adversarial examples over the last couple of years. This is growing almost exponentially. And so as a result, all of you are going to be working on adversarial examples within some time in the near future. Otherwise, this trend can't continue. So, OK, how do we generate adversarial examples? So this here is a plot of the decision boundary of a neural network. So what I'm showing here is each point here corresponds to a particular image, so that this image in the middle is classified as dog. All of the other blue points here are also classified as dog. And I'm going to add one type of random noise in one axis, so that, for example, I get this image here, which is a noisy version of that dog. As I go on the other axis, the same thing happens. I add random noise to get other images that are perturbed. And you'll notice that if I were to draw like a small box around the center, it looks like I'm safe. Everything here is classified the same way, and I think that I'm fine. The problem, though, is that this is just a two-dimensional slice of a very, very high-dimensional surface. I've picked two random orthogonal directions to show this plot in, but there are 3,000 other ones I could have selected. And so the question is, why is it the case that I can still find adversarial examples on neural networks? And the reason is that it turns out that while in these two dimensions I happen to be safe, I can add random noise, and it doesn't really change the classification. For example, I don't really think that the image way up there is an adversarial example. Like it's far too hard to recognize that object as anything as a human. I would like something which is much less perturbed. So what I can do is I can just switch the axis that I'm looking at, sort of rotate this plot through the 3,000 dimensional space, and I can end up with something that looks like this. So I'm adding the same direction of noise on the y-axis. But on the x-axis now, I'm adding sort of the worst case adversarial noise. So that here, this image is now on the other side of the decision boundary. And this really is the fundamental problem of adversarial examples, is that neural networks make classifications where in benign settings you can add lots of noise and they're very robust. But the worst case direction is highly sensitive and can change the classification. Let me do one more thing to this plot, just so I can make it a little more clear what's happening. And I'm going to extend the z-axis up so that the z-axis now is going to correspond to the confidence of the neural network in the correct prediction. I'll say that one more time. So this here is the plot. The confidence is now of the correct prediction as determined by the neural network is now the z-axis. So the initial image is highly confident in the correct prediction of being dog. But you can notice that you're sort of on the face of this mountain. And it's very easy to just find the direction to go down and use gradient descent to find an adversarial example just by walking down the face of this hill. And very quickly you end up with something which essentially is 0% confidence in dog and is now very high confidence in this case, the airplane class. So this is kind of what's going on here with adversarial examples, is that in random directions, the classifiers are good, and in the adversarial directions, the classifiers are bad. OK. So then what do we do with defenses to adversarial examples? So a defense is a neural network with two properties. The first property is that it's accurate on some test set of data. We want the classifier to be good on normal settings still. But we also want the classifier to be robust to an adversary who's trying to evade it. So let me give you a couple examples of defenses that have been considered in the research space. The first example is called adversarial training. This sort of makes the claim that neural networks don't generalize to out-of-distribution data. Adversarial examples are maybe somehow out of distribution. And so therefore, we should train on the adversarial examples to become robust to them. So the way this works is fairly simple. So in normal training, what we do is we take our training data, we feed it into some training algorithm, machine learning happens, and then we get out some function f. This is a classifier which does well on the training data. So now what I'm going to do for adversarial training is maybe the very natural thing. I'm going to take the images that I just had. I'm going to generate adversarial examples for each of them. And now I have these adversarial examples. I'm going to copy them back over to the training data. I'm going to give them the label of what they originally were classified as, and then train on these along with the original training data. And this is going to now give me a new classifier. And then I'll repeat as many times as necessary. Keep on training on the adversarial examples of the old classifier until eventually this converges on something. And the hope is this something that it converges on is robust adversarial examples. So that's one thing you can imagine. There's a second proposal from sometime last year called Thermometer Encoding. And the claim here is that neural networks are in some sense overly linear. That is that if you take the decision boundary, you can fairly easily extrapolate in one direction what the classification is going to look like for a long direction. And maybe this is bad. Why you should think this, there's some theory, but this is the claim the paper makes. And so the proposal is that I'll change the input representation. So for images, typically we represent the input as just a discrete pixel value from 0 to 255. Maybe it's hard for the neural network to learn that a change from 0 to 1 is somehow different than from 250 to 251. So let's make it easier. And what we'll do here is I'm going to create a thermometer encoding function of the input. And I'll say that the thermometer encoding of 0.13 is a couple of ones followed by a bunch of zeros. Maybe of 0.66 is more ones followed by a few zeros, and of 0.97 is almost all ones. And now the hope is that the neural network might be able to disentangle the difference between taking a small step at the low end of the scale and taking a small step at the high end of the scale. Maybe this helps. The final kind of defense that I'll tell you about is input transformations. So the claim here is that perturbations are in some sense brittle. And so what I can do is I can take my image, I can pre-process it by some kind of random transformation, and then feed it into the neural network, and then maybe by doing this, I can get an adversarial example become classified correctly because it's been modified in some way. Now you have to make sure you don't add too much noise that regular images are misclassified, but you want to add enough noise so that adversarial examples are no longer classified correctly. You could also imagine doing other things like JPEG compression, or you could try adding noise, and I'll get to some of these in a little bit later. Okay, so those are defenses to adversarial examples and how they work. Now let me tell you what it means to evaluate the robustness and how it is we go about doing this. So I guess the basic question here is, what does it mean to evaluate the robustness? And what we're trying to do is we're trying to figure out how accurate our classifiers are. In standard machine learning, this is very easy. You take your model, you train the model on the training data, you compute some kind of evaluation function to get the accuracy, and then if it's good enough, then you say you're state of the art, and if it's not good enough, then tune hyperparameters more until it's good enough. And this is a standard thing that is done in all of machine learning. So the question is, what changes on the adversarial example evaluations? And in particular, the only thing that changes is this line, is the evaluation function. So typically, we have some kind of test set that we can use to evaluate a classifier on. And as long as I don't train on my test set, I basically can't cheat in a standard machine learning evaluation. I just need to make sure I train on training data, and it's disjoint from test data. I test on that, and I'm good. The problem is that no test data exists for adversarial examples, because the adversarial examples are necessarily the adversarial examples on the new classifier that you happen to just train, and so that doesn't yet exist. So robustness evaluations basically turn this function of just evaluate on the test data into something that does this, where now we have to come up with some new attack function, which is a function of the model, and then use this to evaluate. Now, there are other ways you could imagine evaluating, but in practice, this is what people do. You take the same test data that you would otherwise test on, you come up with an attack, and you see how badly you can make the classifier do on that test data. Now, there's a couple things I'm not showing here. For example, I do have to constrain that the adversary can't just arbitrarily modify the inputs to make them all black, because then the accuracy would always be 0. So you'll have some threat model that says maybe you can only modify 5 pixels, or maybe you can modify the low 3 bits of every pixel. But once you've done that and can put some threat model down, then this is exactly what the attacks are doing. You're going to try and modify all of the images in the test set to make them so that the classifier is now fooled. Okay, so the question then is, how complete are evaluations that are written in today's papers? And for that, let me give you a case study of the defenses that were accepted at ICLR 2018. ICLR is one of the 3 main conferences on machine learning. This happened sometime last year. So at that conference, there were a bunch of papers that were defenses to adversarial examples accepted. And I should say that, to begin with, the authors of these papers did make a serious effort to evaluate them. I've shown the papers here, and I've highlighted in red the regions that are the evaluation. So by space, most of these papers are roughly 1/2 evaluation. The authors of these papers are from places like Google and Facebook and Amazon. They're from universities like Stanford and Berkeley and Carnegie Mellon and UT Austin and Princeton. So by all accounts, these are highly regarded researchers. They know what they're doing. We reevaluated these defenses, and we placed 4 of them out of scope. These were defenses that had threat models that were incompatible with ours, or that had some certified claim that they could prove that it was robust under some specific distortion model. I'm not in the business of doing proofs, and so we just said, let's put those out of scope. 2 of them were correct. I'll come back to what I mean exactly by correct in a second. And the other 7 were broken. So over half of the defenses that were accepted at this conference were broken, and 6 of these offered 0 robustness. They did absolutely nothing. One of them helped a little bit. And by correct for the other 2, what I mean to say is that the claim that was written in the paper was correct, and we were not able to invalidate it. So I'm not going to say that it's necessarily going to definitely be right, but I'm not confident saying it's wrong. And this is in some sense concerning that they were broken in this way. And not only were they broken in this way, when we broke them, it only took us maybe a month or something to do this for all of these defenses. And so the question is, what was going on? Why is it that these defenses were accepted at one of the top conferences in machine learning, and over half of them were easily broken? So I showed you this picture earlier. This is the loss surface of a neural network, where on one direction I'm going adversarially, and in the other direction I'm moving in some random direction. So it turns out that what happened is that they turned this loss function into something that looks like this. In case it's a little hard to see what's going on, let me zoom in on this one region here and show you that the function looks like this. So imagine that you're a gradient descent optimizer, and I say you're there. Which direction would you like to travel to find the adversarial example? You basically have no idea what to do. You'll pick a random direction. Maybe it turns out that you're on the side of a cliff facing this way, so you step that way. And then it turns out that now you're on the side of a cliff facing the other direction, and you step back. And you run for 100, 1,000 iterations, just randomly moving around this space. If you're lucky, you happen to cross the decision boundary. If you're unlucky, you just don't get anywhere useful. And so this is essentially what happened. Almost all of the defenses that we looked at did something that looks like this, where they made the gradients insufficient to provide insufficient information to actually know in which direction to travel to find an adversarial example. And so you may say, well, that's fine. You can't find an adversarial example, therefore it's robust. But remember that what the loss function actually looks like is this. And so while there may not be an easy way to find it when you look locally, when you look globally, in some sense it's very easy. This function looks nearly identical to this one. And so if I somehow knew ahead of time what the big picture looked like, I could identify which direction to travel in to find the adversarial example. It's just the fact that with this very, very local view that the standard optimizers have, they can't find adversarial examples. Now, one brief aside, this isn't the first time that it's happened that a bunch of defenses are proposed and very quickly broken in the space of adversarial examples. So this has happened relatively regularly over the last couple months, where people propose defenses and very quickly they're broken. More often than not, if a defense is proposed and someone else evaluates it, it's shown to be wrong within a couple months. Now, I should mention that this is not all of them, but almost all of the evaluations that are done in adversarial machine learning on defenses. And so in security, we have this interesting setup where one or two people write a defense paper, and then everyone else wants to write the attacks. For some reason in machine learning, it's the other way around. There are like 20, maybe, attack papers that try and evaluate defenses. And there are something like 300 or 400 defense papers. And this is in some sense a concerning setup to be in because we've only evaluated maybe 50 defenses ever. And the other 450, maybe they do something, maybe they don't. No one knows. And so that's its own problem. OK. So what are the lessons that we've actually learned then from these evaluations? So that, I think, comes in a couple pieces. So let me start with the first. The first kind of lessons is what types of defenses are effective. So the first kind of defense that's effective is adversarial training. This is the first one that I showed you earlier. This is one of the ones that we tried to evaluate, and we weren't able to show that it was not robust. What adversarial training does, so this is the loss surface of a standard neural network. What adversarial training does is it makes the loss surface, instead of look something very ugly like this, it makes it look very nice like this. So it really smooths out the decision boundary. Notice it pushed the decision boundary out. So it's not fully robust. It's not like we solved the problem entirely, but I've made it much harder to find adversarial examples. And this also gives me confidence that I'm not just being fooled artificially because it's hard to find them. In some sense, it looks like it's easier to find adversarial examples in this setting than it was on the standard classifier. And by easier here, I mean, I know that I've done the right thing, because the loss surface is pointing all the same direction the entire way. So probably it's not the case that there's not going to be these weird wrinkles in the loss surface like here. Now, I can't guarantee that, but that heuristically seems like it's the case, and for everyone who's tried to reevaluate these, they found similar results. So adversarial training seems like one good thing. I should mention it's maybe a little bit unsatisfying that the solution to adversarial examples for this defense is just keep training on them until you do well. You may have liked a solution, and I would have, liked a solution that said, here's a system that's better at machine learning because it better captures what humans do or something else. And then section 13 of their paper shows, and also it solves adversarial examples. I view adversarial examples maybe as a bug that should be fixed not by just addressing that, by addressing the root cause. And if the root cause is that they don't adapt to new domains, these machine learning classifiers, then this is kind of cheating. But it does seem like it's correct. So if you know ahead of time what kinds of attacks you're going to see, in this machine learning space, you can just train on those attacks and become relatively robust to them. Now, if the adversary changes the threat model, and now instead of distorting the low 3 bits of every pixel of the image, now flips 5 pixels, the classifier is going to break. So you have to train on every new threat model that you're going to ever see. And enumerating these seems hard. But this is one of the effective defenses. Okay, so the second class of effective defenses is the empty set. The only defenses we have are the first. Everyone who's tried to propose another defense, basically, that isn't adversarial training, so far when anyone else has evaluated it, it hasn't worked. People have tried lots and lots of other things. The ones which have been evaluated don't work. And as I mentioned, there are another 400 that people have proposed that no one else has evaluated. And so we don't know if they work or not. And this is an unfortunate situation to be in. Fortunately, there are a bunch of you in the audience who are all security people who know how to evaluate things. So maybe you can help remedy this. OK. So the second lesson from evaluating robustness. OK. I told you earlier that making the loss surface ugly doesn't work. And I sort of appealed to the fact that if you looked at the pictures, then it's not very different, and it looks like there's an attack, without actually giving you what that attack was. So let me tell you what you can do. So the first thing that you could do to attack this would be to think really hard and then write a differentiable implementation of JPEG, and then backpropagate through JPEG to compute gradients, and then everything works. That's a lot of work, though, because there are lots of functions that are easy to write that have nice forward passes that don't have differentiable back passes. And this is how we compute these adversarial examples, if you remember, is we take gradients through these neural networks. So that's one thing you could do. And this is a very nice solution if you're willing to think very hard about each of them. There's another thing you can do, and we have a paper that shows that you can do this, is suppose that you have a very special type of neural network, which it turns out many things fall into this category of. So suppose that I'm taking my image, and I feed this forwards through a neural network that has some kind of layers that are hard to differentiate through. So most of it is a standard neural network, but it turns out that you can't compute gradients through 1 or 2 small number of layers. So what we'll do is we'll do the forward pass in the standard setting. I'll do the forward pass, and I'll get some probability vector of what the input's going to be classified as. And now, On the backward pass, instead of taking the hard to differentiate through function, I swap it out with an easy to differentiate through function, which is not exactly computing the right thing, but is a close approximation. So for example, JPEG compression roughly satisfies the equation f of x equals x. This is the idea of JPEG compression. It shouldn't change the image very much. The gradient of f of x equals x is 1, so I'll just drop the JPEG compression and pretend it didn't exist. Now, this is not actually the gradient of the function. It's a lie, but it turns out that it's a useful lie. The gradients of this are relatively smooth, and it means that it points you in a helpful direction relatively continuously. It doesn't actually always give you the right answer, but it gives you some kind of gradient signal, so that if you repeat this many, many times, continuously finding a single step of a gradient and then taking a small step in that direction and repeating, with this lie of a gradient, then it turns out that's good enough, and you can actually find adversarial examples this way. And so this is one general way that you can find adversarial examples. There are others, and I would encourage you, if you're interested, to go read the literature. It's very interesting. But this is one of the standard ways now that you can differentiate through things that break gradients in this one particular way. OK, so the third kind of lesson from performing these evaluations is this. So I should mention, this is all going to be from this paper that we wrote called On Evaluating Adversarial Robustness about 6 months ago now. That's basically a set of advice on how you should perform adversarial evaluations. So what I'm going to do is I'm going to cover a bunch of things that you shouldn't and should do when performing adversarial evaluations. For those of you who aren't performing those evaluations right now, maybe this part isn't as important for you, but again, I would encourage you to just see what it is that's happening in the space and the kinds of errors that are being made, partly because many of the errors that are being made are very basic, and I would like more security people to be working in this space, because I feel like many of us would not make these same kinds of errors. The other thing I'm going to say is that I want to give some actionable advice here, and that requires me being specific, so I'm going to give screenshots from papers that do the wrong thing. Just know that this is standard, and I'm not bashing those individual papers. I'm sort of showing the types of things that have gone wrong in the past. OK. So the first thing that I'm going to say is that in order to do a security evaluation, you actually need to do a security evaluation. You have to take the defense and try and beat it. It's not sufficient to go and generate adversarial examples on some model, save them to disk, and then say, OK, I'm going to now train some new model on some new data with my defense, and then test them on the saved adversarial examples that broke the other thing. This doesn't work. I mean, you all know this. It's not fine. If I developed a new crypto algorithm and said, well, let me take the differential that breaks MD5, and I'll apply that to mine, and it fails, therefore my cipher is secure. I mean, this would be ridiculous. But this is what's done in maybe half of all adversarial example defense evaluations, is people don't actually try and evaluate on it in an attack their defense. So this is the first thing that you shouldn't do when performing an evaluation. The second thing is that there are some papers that are a little better. They have like a section 3.1 called effectiveness, which is a page and a half. By the way, machine learning papers are 8 pages long, so a page and a half is actually a relatively large fraction of the paper. And so they have this effectiveness section, and then they have another section, 3.4, that's robustness to the white box attacker, which is a paragraph long. In which case, what was this section doing? This section was showing that if you take someone who doesn't try very hard, then it's robust. And to which I would say, take this, put it in an appendix. Good to know that someone who doesn't try very hard can't break it, and make this the remainder of the paper. So this is something that's fairly typical, is you'll see a very, very long section on it stops all of these attacks when you don't actually try, and then we'll try a little bit for one paragraph. OK, in machine learning, there's this thing called a held out data set. This is where you take some data and don't test on it until the very end. You can't hold out attacks. That's just a concept which doesn't exist. You need to come up with new attacks. You can't just take some attack, pretend we didn't know about it before, design our defense, and then run that attack in particular against it. That's not an adaptive attack. Okay. There's this attack that's called FGSM. What this does is it takes one step of gradient descent. It was designed to show that neural networks are linear. It was not designed to evaluate defenses. But because it's only one step of gradient descent, it's very fast and very easy to write, and everyone uses it for evaluations. Don't. If you want to run against it, that's fine. But it would be nice if you also ran against stronger things that tried harder than taking one gradient pass through a neural network, and so that you can evaluate in 20 milliseconds instead of half a second. In particular, when performing gradient descent, it's necessary in general to perform 100 or 1,000 iterations of gradient descent to do these evaluations properly. You can get by with doing fewer than 100, but you have to think really hard. You have to make sure that every gradient step is actually doing something useful to give you an adversarial example. And this takes a lot of work. It's much easier to think less and make the computer do more work and just make it perform many, many, many iterations of gradient descent and give you something which is mostly going to correctly evaluate if you're robust or not. You should check that when you do more work, you actually get better. If you try a very weak attack, in this case FGSM, one iteration of gradient descent, and it is doing better, so the accuracy under this attack is lower than the accuracy when you try many, many, many iterations of gradient descent, probably it's because you've done something wrong. If you're trying harder and succeeding less often, then you're optimizing for the wrong thing, probably. And so this is one of the other things to check for. And the final thing to check for, I think, is that you need to make sure that if you run an attack that has no bound on the distortion, then eventually it should succeed. So why is this the case? Well, if I took some image that's a cat, and I allowed you to make an arbitrary distortion to it to turn it into a dog, in the limit, it should just turn this image into a dog. And if it doesn't do that, then you know that your attack is weak. Because if it fails, then it means it's got stuck in some kind of local minima that isn't actually an adversarial example. And so by making sure that when you run it for long enough that you eventually succeed, then you can at least have some confidence that it's doing the right thing. This is related to this point, which is that, also let me show you, this is some plots that people have made of distortion on the x-axis and how well the attack has succeeded on the y-axis. And in particular, all of these are plateauing at 10%. If I give unbounded distortion, I should succeed 100% of the time. And so it's concerning that they're all plateauing at the same value of 10%. Probably something is going wrong here. Maybe it's more exaggerated in this plot, where on ImageNet with 1,000 classes, so the best you could hope if you had a random classifier would be 0.1%. The strongest attack that can turn any image into solid gray with distortion 128 over 255, that's this point here means, is only succeeds here slightly over 20% of the time. So something's going wrong with these kinds of attacks. Make sure this doesn't happen. It's also true that if you make the threat model more broad, the attacker should succeed more often. This is kind of true by definition, but it's not true here. Just check for these simple things in these evaluations. And this is something that sort of regularly occurs, is that you'll give the adversary more power and they'll succeed less often, which is a little weird. Okay, so maybe enough negative things. Let me tell you some good things that you can do in these evaluations. The first of them is to evaluate against the worst attack. So if you pick 10 attacks and evaluate against all of them, and one of them that's very weak shows your thing doing better, and one of them that's very strong shows your thing doing worse, your defense is worse. It's not okay, and this paper does that nicely. So it evaluates against a slew of attacks and then compares against the one that is most effective. I really like these accuracy versus distortion plots because they help me debug whether something's gone wrong. And so here you have a very nice example of adversarial training that's supposed to be robust up to distortion 0.3. And you see that it is robust up to 0.3, and then as soon as you exceed the threat model that was defined and go above 0.3, the accuracy begins to plummet. This is a nice thing to see that hopefully they've done the right thing now because it eventually goes to 0 and it only gives you what it's supposed to. The other thing is that you have to actually verify you've done enough iterations of gradient descent. I mentioned earlier that maybe 100 or 1,000 is good. Turns out sometimes it's not. And here's some defense that these people ran where they were still getting improvements in attack success rate when going from 100,000 to 1,000,000 iterations of gradient descent. I don't know what's going on here, but I'm really glad they ran this experiment. And so it's really nice to see these kinds of results. And finally, or maybe second to last, is that you should try something that's gradient-free. All of the other things that I told you earlier are gradient-based attacks. These are attacks that sort of look which direction on the hill is down and go that way. There are other kinds of attacks that aren't gradient-based that are good to also run, because if you break the gradient descent, then it won't break these kinds of attacks. And that's a nice kind of thing to know. And maybe the final kind of simplest thing to do is to just try random noise. So if you're not robust to random noise, you shouldn't be robust to adversarial examples. And there's a little bit of theory that shows this. And so in particular, all of the defenses that we had evaluated earlier, that we had to work for a couple months to break, turns out they all perform exactly the same if you give them classified random noise. And so this is not something, this is sort of a very easy, simple test to see if you might be robust. And I should mention that the one blue line that's way up there is training on exactly the kind of noise that we happen to test on. So that's not really a defense, that's the upper limit of what you could hope to achieve, and basically all of the classifiers do the same, which is much worse. Okay, so that's all I have to say about what we've learned from evaluations so far. Let me briefly mention what I think will happen in the future, or what may happen in the future. So I showed this slide earlier of lots of things being broken. Okay, so the year is 1997. The AES contest is going on. We're trying to design robust crypto in block ciphers. And you see a slew of papers coming out that's like break after break after break after break of things that are no longer effective. Are you thinking like we're hopeless?
They're all written by David Wagner.
These ones are all written by David Wagner, yes, because I went to his website and downloaded them because he did a lot of them. Yeah, so, right, so if we were in the 90s, should we think that we're hopeless? And if we go back to like today, this is now the best attack on AES, which is like almost 10 years old, and it's not even really effective. So like we went from a time in 20 years where everything was broken to designing relatively good crypto, and so maybe you think are we crypto in the 90s? Maybe we have the right kind of thing that we're doing. We just need to think a little harder, and maybe we'll solve the problem. Okay, so I'm going to argue maybe not, and I think I have two reasons why the answer is maybe not. Okay, so the first reason is something like this. So this is a plot of the best certified accuracy with a proof that you can get on ImageNet today. So these people can write down a proof that says that the accuracy on the classifier is at least some 20% when you go up to this distortion bound. So attack success rates in security, and this is a slide I stole from Dave Evans. I think it's a wonderful slide. So in crypto, we say that we're secure if we have a probability of succeeding of like 2 to the minus 128, roughly. If something's 2 to the minus 127, it's broken, run for the hills, throw it out, try again. Okay. In systems, we want 2 to the minus 32. You'll do a stat canary, something like this, but it's okay, maybe broken is 2 to the minus 20. Try a million times and you can defeat a stat canary, maybe that's a broken defense. In machine learning, we're like 2 to the minus 1. Like the best defenses succeed half of the time. And something's broken if it's 2 to the 0. So we kind of have a long way to go before we can maybe call this a nice kind of security. Okay, so that's maybe one reason why we're not yet crypto in the 90s. The other reason is that I showed you this plot of how much we can prove that we're accurate for. These are the images that correspond to the proofs that we can be robust. So I can prove that there's a 10% chance that I'll classify this image here correctly. I can't really tell the difference between those two images. And so, maybe we still have a bunch of work to do. In particular, maybe I'd want the plot to look something like this. And if I were to extrapolate those lines, I'm down to negative 1,000 over here. But it's in some sense even more concerning than that. So this is the original image. This is an image that has an L2 distortion of 75. L2 distortion is one of the threat models people consider. This is the standard Euclidean distance of how much distortion I'm adding. And I would like to be able to classify this image correctly. I think all of us can get it right. I've added a little noise, but not so much that it's impossible to see. But it turns out that this image here also has an L2 distortion of 75. And so we don't really even have a good definition of what we want. We know intuitively we want to do something like the human does, be robust in some sense under some norms. But we don't actually know what norms we want. Now, it's OK for today that we're using these L2 norms, because we can't even solve them. And so in particular, if I set a really small bound, then it's clear that a human wouldn't change their mind. And so we should at least be robust under these small norms. And so I'm not saying don't work on this space because these norms are bad. The norms are in some sense the best we have today. But if we want to succeed in the future, we can't hope to succeed by focusing only on these L2 norms. So maybe the claim is we're crypto pre-Shannon. Crypto pre-Shannon was people trying the best they could to come up with defenses that worked, but they didn't really know what they were optimizing for. And then Shannon came about and told us about entropy. And now we had something to talk about. And we could point to something and say, this is what it means to be secure. It would be nice in the space of machine learning security to have something to point to say, this is what I want to be secure. I don't think that we yet have that today. And without that, I don't think that we have any hope of achieving general robustness. OK, so to briefly conclude then, I think we've come a long way to understanding adversarial robustness. A couple years ago, we had basically no idea how to perform evaluations in the first place. Now, at least, we know how to perform the evaluations. So that's good. But I still think we have a long way to go in order to be able to achieve actual general robustness. Because I don't think we know what the correct distortion models are. I don't think we actually know what we're optimizing for. But my hope is that the lessons that we've learned from how to evaluate correctly will help us actually succeed in this general quest for robustness. So thank you, and I'm happy to take any questions.
Thank you very much, Nikos. Any questions? There is a microphone at the center of the room. OK, well, I'll start with one question. So it seems like what you presented is more from the perspective of authors. But I think half of, if you want to call it blame, goes also on reviewers. They let this paper go through.
Yes.
So can you turn whatever you suggested into do's and don'ts for reviewers? Check this, don't check that.
Yeah, so what about reviewers? I'm not trying to blame anyone. I'm just trying to comment on the state of research today, I guess. Now, it is a problem that these papers maybe get accepted. But yeah, OK. So to answer your question directly, for reviewers, I think the necessary thing is to check that the people have tried hard to break their own defense. This is, in some sense, the only thing that matters. So I should say that I don't expect reviewers to only accept perfect defenses. This is something you can't do. The bar that I set for an adversarial example defense paper is convince me that no existing attacks will defeat it. It's sometimes a low bar. But convince me that in order to defeat this, someone will have to think of something new and interesting that is publishable. Because if you can sort of pass this bar, at least we make sure that it's not the case that in order to break something, I download your code, if you've put code up, which you should, And then I go take some attack implementation and download that, run the known attack on the known defense, and that thing breaks. And then like we've learned nothing, everyone's wasted their time by reading your paper and reviewing your paper. Like it would be much nicer if I had to think really hard and come up with a new technique in order to break the new defense. And I think that's what reviewers should be looking for is, can I convince myself that in order for this to fail, I'll have to learn something new about the world? That's my bar.
That's a good answer.
Hi, I was wondering that in some cases where you have a high modification distance or L2 norm or even proportional like mean average error, at some point it's impossible for a classifier to classify this when you mix adversarial examples in due to catastrophic interference. At what level do you think it's realistic to expect a classifier to be able to differentiate those?
Yeah, at what level should a classifier be able to, what level of noise should a classifier be able to correctly classify adversarial examples? This is, I think, one of the big unknown questions. I know how to pick images that are very close to humans that are still classified wrong. If we could get those all correct, I don't know at what level we would want things to be actually be correct. Like I showed this image earlier of one way one example of images that were L2 distortion 75 apart that I would want to become classified correctly. So that's clearly in the set of things that humans perceive similar. But then there's also this other image where you draw a big giant box over it, it's the same. That's outside the set. Like in some sense, I think coming up with a function of would a human think these images are similar may be just as hard as coming up with a function to do the classification correctly. Because if you had that image, if you had that magic classifier, maybe you could just do k-nearest neighbors. But yeah, I would like to see more research on this question in particular because in some sense it's necessary. I'll give one other comment, which is that in some areas, it's not the human oracle that matters. So malware classification. I don't care what the person thinks about whether or not this is malware. Either it deletes my hard drive or it doesn't. And so the oracle here is it malicious or not? And the distortion model is maybe anything goes. And so there, it's even harder because you kind of have to be correct everything. Maybe you can assign some kind of cost function to how hard it is to do attacks, but I think the vision setup might be different from the audio setup, might be different from the malware setup, might be different from the text setup, and we'll have to think carefully about each of those.
Thank you.
Yeah.
Thank you. Thank you, Nicholas.